along the atomic arrangements. Okay, this free electrons is not really free. It has to move inside these different potential energies, not just the ground state or equal energies, equal potential energies. So it has to travel a periodic potential, different potential. So it is not really free. Not really free, but almost free. Right? Because it is not belonging to any one specific atoms. Now, what in this chapter, what we are going to see is that what's going to happen if electrons are confined in a solid, this many electrons, and this many electrons has to follow the Pauli exclusion principle. Then what's going to happen? We want to know what kind of energy is this available for these electrons, the free electrons, okay, in this sense. And we want to know what is the density of that energies. And finally, we want to know actually these electrons, what the probability of these electrons can really have that energies. So you have to think carefully. What we are going to do here is that first we want to find out what kind of energies, what kind of energies available for free electrons in a solid. This is the first thing that we are going to do. And then next thing that we have to do immediately after this, is that what is the density of available energies? Okay? What is the density of the available energies? This is the available energies. Okay? And then finally, the free electron energies. What is the free electron energies? Actually, these available energies, the electron, what is the probability of electrons to occupy that available energy state? This is what we are going to do in the third stage. Okay? First, we want to find out what kind of available energies really exist in the solid for the free electrons. And then finally, we want to know what is the probability of electrons to occupy that available energy state. Then we end up with the energy states of the energies of the electrons in a solid. So finally, the final goal is, of course, we want to know what is the energy of free electron in a solid. This is the question we want to answer in this chapter, okay? So if you just follow the text, then you're going to see that for the first one, what kind of energy is available for the free electrons? We know the Schrödinger equation, right? What the Schrödinger equation says is that this is the Schrödinger equation, 2m over h bar square equals 0, okay? You want to specify this equation in the 3 dimensions, Cartesian coordinate x, y, z, and then, you know, the eigenvalues is going to be represented something like this. That is the energies total. And then eigenfunctions, if well, this is the separable function, so that this is the wave function is going to be something like this. The eigenvalues and then eigenfunctions. So you just extend this Laplacian to have this, and then you can have for each functions we know we have driven this, the x, for example, the wave function, we have answers something like this, right? Sine lnx pi x. Okay? We have these solutions. And then this is the normalization factor for that to make this wave function as a probability, right? And then the energy eigenvalue, we have driven this s square h bar square pi square or nx square, something like that. So in a normal case, the L is going to be 10 to the 7th or so, when it's this is the order of 10 to minus 14th in a normal case, right? But if you decrease this L in the atomic level, this is going to be about 30 electron volts. The gap, energy gap, becomes 30, like around the 30 electron volts in an atomic scale. So we have seen this. Okay, the energy gap becomes very large. So if you put that thing into here and then this thing into here, then you're going to have, for example, energy state nx, ny, and z is going to be h bar square pi square over 2m L square nx square plus ny square plus ng square, something like this. All right? And then this energy is nothing but the h bar square over 2m and k vector, something like this. All right? We know this is corresponding to this. The energy is going to be represented with the k vectors. This k, of course, is the kx, ky, kz wave number, or it can express in the n digit space, n space, something like this. And you notice that this is the sphere radius. There's simple equations related to spheres, right? So in the text, the minus sign is not going to be, it doesn't have any meanings. In nx, ny, and ng space, you just put the positive numbers only, and then all you have to do is, if you want to calculate, if you want to know what is the available energies that the free electron can have, according to the Schrödinger equations, then all you have to do is just to find the volume of this. Because the n energy state is going to be represented in the spheres. Equations, something like that. Okay? So, it's a simple. Okay. If you, let me just put this thing into K-space a little bit. In this volume thing, you have to think about the degeneracy. Degeneracy. Which means, for example, E111, nx equal to 1, ny equal to 1, and z is equal to 1 is going to be called E11. In this case, the energy is 3h bar square pi square over 2ml square, right? And then 2 to 2 case is 6h bar square pi square over ml square. So it is a non-degenerate state. But if you think about the nx, ny, ny and z is equal to 41 h bar square pi square over 2 ml square. Then for that 41, you can have a ninefold degeneracy, like nx, ny, ng can be 1, 2, 6, 1, 6, 2, and 2, 1, 6, 6, 2, 1, 6, 1, 2, 4, 3, 4, 3, 4, 4. Something like that. 1, 2, 3, 4, 5, 6, 7. Well, how come I'm missing something? 1, 6, 2, 2, 1, 6, 6, 1, 2, 1, 6, 1, 2, 4, 3, 4, 4, 4, 3, 4, 4, 3. We're still missing one. Oh. It got to be threefold. 1, 2, 6, 1, 6, 2, 2, 6. You guys figure out. What is missing? 6, 2, 1. 6, 1, 2. 2, 2, 6, 1. Okay? So it is a ninefold degeneracies. All those different configuration of nx, ny, and g we're going to have the same energies, the 41. We call that the degeneracies. Anyway, the next thing that we have to do is, this is the available energy energies that a free electron can have in a solid. Now, how can you calculate? We cannot count all those things. All we have to do is just to find the volume of this, but in order to find the density, we do a little trick on this. Energy density, energy state density. We really don't count it in order to calculate the energy state densities. Now, Ne is the density of allowed states, okay? And then NE/DE is just a number of allowed states between E and E plus DE. All right? Then, now here's the trick. N prime EDE, we just make that. Then this is the number of energy states less than energy E. Okay, this is very important. We want to get this because when you try to find the NE, it's going to be dN prime E over dE. If you make a derivative of this, then you're going to have a number of allowed energy states, Ne. Okay? So, in order to have these equations, you just set this M prime, and M prime in a physical sense, it is nothing but an integration of N prime E is nothing but the energy from 0 to E and Ne over dE, okay? That is the number of energy states less than energy E, okay? So, if this is okay, then we can directly think that if you make a derivative of this, then we get the Ne, right? So, this is a new idea, and this is kind of trick that to really count the number of energies, which is a density of energies, okay? And E, Nx, Ny, Nz, and let's note we have seen that Em L square, Nx square plus Ny square plus Ng square, okay, Ng square Ng square. So Nx square plus Ny square plus Ng square is going to be 2m L square E over h plus square pi square. So this is the radius. Okay? So in an n space, as shown in the text, we have a 1/8 of the square volume is going to be the number of available is the available energy states, and then in order to count that to find the density, all you have to do is just to find the volume corresponding to that the sphere, 1/8 of the sphere. Now the n prime E is going to be 1/8 Okay? This is the energy, remember, this is the number of energy states of which energy is less than E. Okay? So that is going to be 1/8 of the sphere, which is 4 pi over 3, and then the R third. And then that R is going to be square root of this. Okay? So you put the square root of this, and then put that R here. Then you're going to find the volume. And then this is the L third 2m over h bar square 3/2 and E 3/2. That is the n prime E. Now, if you take into account of spin, then you have to multiply this thing by 2, okay? That's all you have to do. And then n prime E is going to be 1 over 2 pi square 2m h bar square and 3/2 square root of this, and that is per volume. Here the volume is L cube. Okay? This is the per volume. So you take a derivative of this m prime E with respect to energy E. Okay, then you finally get n E. Okay, now it is not m prime E, and then that is 2 pi squared 2m over h bar square 3/2 square root of energies. And that is a really simple figure. Like this is the energy density, available energy state density. Okay? This is the available energy states density for free electrons. And then if you plot that thing with the energies of electrons,